Good morning, our students, and welcome to the continuation of our class or classes on Poisson distribution. We have just taken a class on Poisson distribution that bordered on introduction of a Poisson distribution, explanation of the PMF of a Poisson distribution, the range of a Poisson distribution, and we equally took some questions on Poisson distribution. In this class, our interest should be on how we can prove the expected value and then the variance of a random variable that follows a Poisson distribution. So we are talking about expected value and variance. Expected value and variance of a Poisson random variable. Permit me to write this as random variable. So first of all, we are going to start with the expected value. And then we give the conventional way, or we give the expression of expected value of any random variable at all. Whether it is Poisson, whether it is geometric, as long as it is a discrete random variable. So it is expressed as that my E of x is given as sum over the range of x, P of capital X is equal to small x. This is how to write the expected value of any random variable x that is discrete in nature. That's the reason I am using the sum here. But we are discussing expected value of a Poisson distribution. And in our previous class, we already had given that the PMF of a Poisson distribution is given as P of capital X is given as small x equals lambda raised to power x exponential minus lambda all over x factorial, where this x takes a value 0, 1, 2 down to infinity. Therefore, if I want to discuss expected value of a Poisson random variable x, this P of capital X equals to small x is going to be replaced with P of capital X equals to small x of a Poisson random variable x. And it becomes, therefore, what I have now is that E of x, which is now expected value of a Poisson random variable x, is now given as, here I have sum. I am now clear that the range begins from 0 to infinity. So I say x starts from 0 to infinity. Here is my x. Then instead of writing P of x equals small x, I will replace with this. So this lambda raised to power x exponential minus lambda all over x factorial. If you watch closely, you find out that this exponential minus lambda does not contain x. So it is a constant in this function, and it can be brought outside the sum or the summation. So this thing becomes, this equals exponential minus lambda sum x is ranging from 0 to positive infinity of this x that is here, x, then of lambda raised to power what? X, all over x, all factorial. We want to make effort to remove this x that is here. So for me to remove this x that is here, let me expand this x factorial. And what I have becomes that this equals, we have exponential minus what? Lambda sum that x begins from 0 to this infinity of this what? X, lambda raised to power what? X, then we have all over. Here is going to become x into x minus 1 all factorial. What I expanded is this x factorial. So that this x that is here will cancel this x that is here. And what I have left is, what I now have left is what? This equals exponential minus lambda, which is what I have here, sum x is ranging from 0 to positive infinity. This x is already gone, so what I have is what? Lambda raised to power x all over x minus 1 factorial. X minus 1 all factorial. Then I can decide to say let. I can decide to say let. And before I say that let, I want to ask you a question. I have here lambda raised to power x. I want to ask this lambda raised to power x, whether it can be written as lambda raised to power 1 multiplied by lambda raised to power x minus 1. Of course, this and this are the same thing because the base here is lambda, the base here is lambda. Multiplication in indices, you take one of the bases and you add the powers, then you return to this. So they are the same thing. So I can then decide to remove this lambda raised to power x and replace with this. Since this and this are the same thing, so it becomes this equals exponential minus lambda sum x is ranging from 0 to infinity. Instead of writing this, I'll write what? Lambda multiplied by what? Lambda raised to power x minus 1. This is 1. Then I have all over x minus 1, all factorial. Now, if you watch, this lambda equal here does not contain x. So it can be brought outside the sum. So it becomes what? Exponential minus lambda, lambda raised to power 1, sum, then x is ranging from 0 to infinity of lambda raised to power x minus 1 all over x minus 1 all factorial. At this point in time, we can say let. We can say let x equals x minus 1. Let s be x minus 1. So in that case, x plus 1 equals what? X. That is by bringing this one here and making this x subject here, it stands here. So what's actually going to happen is, anywhere I see x in this expression, I am going to use s plus 1 there. And anywhere I see something like x minus 1, I am going to use what? S. So I'll say, therefore, this equals exponential minus lambda for what is here, lambda raised to power 1 for what is here, sum, here is my x. What I'm now going to use there is s plus 1. So I have s plus 1. Here is equal to 0 up to infinity. Here is my lambda, so I have lambda. X minus 1 is already s, so I have s all over. X minus 1 is already s, so I have s factorial. Unfortunately here, we are having s plus 1. And if you watch what we have here, we have x equals to 0. So we have to do something here, so that the range of this x begins from what? From 0. And of course, you know that this can be written as this. This exponential minus lambda, lambda raised to power 1, sum, bringing this 1 over here, what you are going to have is s is equals minus 1 to positive infinity, lambda raised to power s all over s factorial. Okay? Now, what I have here is minus 1, but I want it to start from what? 0. Because the range of a Poisson distribution begins from 0 to start with. So what I'm going to do here is, I am going to add 1 here, but remember that anything I add to the range, I will equally need to subtract it to make sure that I didn't change the range. Here, because of this minus 1, if I add 1 here, it is going to be 0. But when I add that 1, I'm going to subtract it from here. Otherwise, I'll be adding something to the range, which of course is deviating from what we are doing. So in that case, I'm going to have what we call exponential minus lambda, lambda raised to power 1, sum, s is now beginning from 0 because I've added 1 here. I need to remove it here. So this is infinity minus 1. We have lambda raised to power s all over s factorial. And it is important for us to note that when you subtract anything from infinity, it is equal infinity. So this infinity minus 1 is just infinity. So this thing still implies that what I have is exponential minus lambda, lambda raised to power 1. Then we now have sum that s is running from 1 to infinity. Then we have lambda raised to power what s all over what s factorial. Please look at where we began. So it can permit me to clean here and conclude that proof there. Okay? So permit me to clean here and then clean this place. So I will now begin from this. So what we now have that this becomes what? Exponential minus lambda, lambda raised to power 1, we open the brackets. This is 0 this. When s becomes 0, what I have here is lambda raised to power 0 all over 0 factorial, which is 1. 1. When s becomes what? 1, because it begins from 0 to this. When it becomes 1, here is lambda raised to power 1 all over 1 factorial, which is plus what? Lambda. When s becomes 2, here is lambda raised to power 2 all over 2 factorial. I have lambda raised to power 2 all over 2 factorial. Here is lambda raised to power 3 all over 3 factorial plus up to that. And using the Maclaurin series, we are told that lambda 1 plus lambda raised to power 2 all over 2 factorial plus lambda raised to power 3 all over 3 factorial can be given as lambda raised to power exponential lambda raised to power what? 1 for this one that is here. Then multiply by, here is going to be exponential what? Lambda. They told us in that series that anytime we have 1 plus lambda raised to power 2 all over 2 factorial plus lambda raised to power 3 all over 3 factorial down to infinity, that the thing is the same thing as exponential lambda. And here I have that this now is equals, here there is exponential, here there is exponential. I will pick one of the exponential. This is exponential. Here is minus lambda, here is plus lambda. So I have minus lambda plus lambda. Then multiply by lambda raised to power 1. Minus lambda plus lambda will give me 0. Multiply by lambda raised to power 1. Anything raised to power 0 is 1. Multiply by this lambda. This becomes what? Lambda. So the expected value of a random variable x that follows Poisson distribution is given as a lambda. That's what I want you to pay attention to. Okay? Expected value. And look at now the steps of what? Of the proof. These are the steps of the proof. So if you have any challenge in this proof at any stage, quickly drop your worries in the comment section so that we can react to that. Okay? Thank you very much. We are going to go over to the variance of a Poisson distribution, believing that you have understood how we arrived at the expected value of a Poisson distribution. So permit me to clean. So we now enter into what we call the variance of Poisson distribution. Variance of Poisson distribution or Poisson random variable. Variance of Poisson random variable. First of all, we give the expression of the variance of any random variable before we begin to talk about Poisson. And then the expression for the variance of any random variable is given as the var of x, var of what? X is given as e of x all raised to power 2 minus e of x all raised to power what? 2. Okay? We now say but e of x raised to power 2 is given as sum over the range of x raised to power 2 P of capital X equals to small x. This. Okay? Now, when we had here to be only x, it was only x that is here. That was here. Then now we are discussing x raised to power 2. What I have here is now x raised to power 2. This is the expression for any random variable x. But we are now talking about a random variable x that follows Poisson distribution. So if I come here, I am going to remove this P of capital X equals x and replace with the PMF of a Poisson distribution. So I will say therefore, my E of x raised to power 2, which is now for Poisson, is given as sum over the range of what? Remember that the range of a Poisson distribution is from 0 to what? To infinity. So x is running from 0 to positive infinity. Of x raised to power 2, we have lambda raised to power x exponential minus lambda all over what? X factorial. And in this proof, I want you to understand that there is no difference between x raised to power 2 equals x into x minus 1 plus what? X. If you open the bracket here, you have x times x squared, x times minus x plus this x. You find out that minus x and plus x is going to cancel off and you are left with x squared. So this and this can be used interchangeably. In that case, I can decide to remove this x raised to power 2 here and replace with this. And when I do that, what I'm going to have becomes that E of x raised to power 2 is given as sum. The range is from what? X is running from 0 to positive infinity. Instead of writing this, I'm going to write this. X into x minus 1 plus x, close it. That is for this. We have lambda raised to power x exponential minus lambda all over x factorial. All over x factorial. I am first of all trying to solve e expected value of x raised to power 2. So that at the end I will bring it here. So this is equals, we have, I want to open a bracket. By using this, there is plus here. So I want to use what is here. Multiply this quantity. Use what is here. Multiply this quantity. And this thing becomes sum. X is running from 0 to positive infinity of x into x minus 1, which is this one, multiplying by this, lambda raised to power x exponential minus lambda all over x factorial. The sign here is plus. I will equally use this to multiply this, and this sum is also coming in. Sum x is ranging from 0 to what? To infinity of x lambda raised to power x exponential minus lambda all over x factorial. And if you check, what I have here is the expected value which we proved earlier. And when we proved that expected value, what we got the whole of this thing was what? Lambda. So I can equally say that this is equals sum x is running from 0 to infinity of x minus 1 lambda raised to power x exponential minus lambda all over x all factorial plus what? Lambda. Because we proved this in the whole of this in earlier and we got a lambda. Now, like I did before when I had this, I said that the interest is how to we need to remove x. Here, my interest is how to remove x and x minus 1. But if you watch, you find out that this exponential minus lambda does not contain x. So I can bring it outside. And bringing it outside, what I'm going to have becomes. What I'm going to have here becomes bringing this exponential minus lambda outside. I have exponential minus lambda sum x beginning from 0 to infinity of x into x minus 1. Here is lambda raised to power x all over x all factorial. So I want to remove this x into x minus 1. So I will expand this. So this becomes exponential minus lambda for this. Sum x is running from 0 to infinity of this what x into x minus 1 lambda raised to power x all over. Expanding this, I'll have x into x minus 1 into x minus 2 all factorial by expanding this x factorial. So that this and this can go and this can go. And I'll be able to have that this equals exponential minus lambda for this sum of x running from 0 to infinity. What I have now becomes what? Lambda raised to power what? X all over. Now I have x minus 2 all factorial. Okay? Now there is equally something I want to say with regards to this. With regards to this thing. Now I can say, or I can ask you, if somebody have this lambda raised to power what? X. It's the same thing as lambda raised to power 2 multiplied by lambda raised to power x minus 2. I want to have here just this, the way I have this x minus 2 here. Because if you now come over here and you want to know where I arrive at this, lambda raised to power 2 multiplied by lambda raised to power x minus 2. Lambda and lambda common base. You pick one of them. Once you pick one of them, you can then add the powers. And by the addition of the powers, you arrive at this. So I can use this and this interchangeably. And in that case, what I have is exponential minus lambda sum of x beginning from 0 to this infinity. Instead of using this, I'll use lambda raised to power 2 multiplied by lambda raised to power x minus 2 all over x all factorial. If you watch, this lambda raised to power 2 is on its own, so I bring it outside. Bringing it outside now will imply exponential minus lambda raised to power 2 sum x is running from 0 to infinity. What I have is now lambda raised to power x minus 2 all over. Please, this is here what I have is x minus 2, please. X minus 2 all factorial. So all over x minus 2 all factorial. Okay? So what am I going to do here? I can say let, like I did it before, let s equals x minus 2. This thing implies that s plus 2 is equals x. So that I will come back here, anywhere I see x, I use s plus 2. And anywhere I see x minus 2, I'll use s. So this thing becomes exponential minus lambda for this, lambda raised to power 2 for this, sum, this my x has become s plus 2. So s plus what? 2 equals 0 to positive what? Infinity. Here becomes lambda raised to power s all over. Here is now s. We have s factorial. Remember that thing we did before? For this s to begin from 0, because when we bring this 2 over here, it becomes minus 2. So we need to add a 2 to make it begin from 0. We subtract that 2 from infinity. And 2 minus infinity is still infinity. So the whole of this thing still becomes, this equals exponential minus lambda for this, lambda raised to power 2 for this. Then we have sum, our s ranging from 0 to positive infinity of lambda raised to power what? S all over s factorial. And we have shown earlier that sum s beginning from 0 to this of lambda raised to power s all over s factorial using that series is exponential lambda. So the whole thing becomes what? Exponential lambda dot lambda raised to power what? 2 dot exponential what? Lambda for the whole of this one. So this thing is now going to be lambda raised to power what? 2. Which means e of x raised to power 2. And remember, we drop this one here. We should be careful because we still have this one here. We still have plus lambda here. So this is plus lambda. So this is plus lambda. So here we have plus lambda. So here we have plus lambda, sorry. So here we have plus lambda. So here equally we are going to have plus lambda. So here plus lambda, here must be equally plus lambda. Plus lambda. Then here we must equally have plus lambda. Please. Here we must equally have a plus lambda. It implies. So here we must equally have a plus lambda. So this is going to give us lambda raised to power 2 plus lambda. Please, what we skipped was this lambda here. That's what I'm adding them here. Remember that we arrived here, we said that the whole of this thing is lambda. Then I came as a continuation and picked only this one and began to solve, dropping this lambda. So that's the lambda I'm including here. Lambda. Here is equally going to be that lambda. So here is lambda, here is lambda, here is that lambda, here is that lambda, then here is that lambda, and then this one alone is lambda raised to power 2 is this. So finally, you now know that for us to solve the variance, we have gotten that the whole of this one is lambda plus lambda raised to power 2. So we now come here and say therefore var of x equals, in place of this, I'll write what? Lambda raised to power 2 plus lambda minus here. What is inside this bracket here is expected value. And we had earlier proved the expected value of a random variable, x. And then we got it to be lambda. So what I have inside here is what? Lambda, all raised to power 2. What inside is lambda? This raised to power 2 is here. I have lambda raised to power 2 minus lambda raised to power 2. So this and this will go. And we said that var of x equals what? This lambda. So in Poisson distribution, therefore, in Poisson distribution, E of x equals lambda. And var of x equals what? Lambda. Very important to note. And this is how to go about the proof. Just gradually you arrive at it. So what we had here is the proof of the expected value and variance of a Poisson distribution. It is important for us to know that when they ask you what is the expected value in Poisson distribution, the answer is the rate of occurrence of the event of Poisson distribution. If they ask you the variance of a Poisson distribution, it is still the rate of occurrence. So the question we solved when we had the introduction, where they said that the rate of occurrence of a course going through MTN network is 10 per hour. If they ask us the expected value there, it is 10. The variance there, it is 10. Thank you very much for your audience thus far. And do remember to subscribe to our YouTube channel to follow our classes. Thank you very much. The next we are going to have now is going to be on the moment generating function and then the characteristics function of a Poisson distribution. At the end of which we begin to talk on what we call the Poisson approximation to binomial distribution. Thank you very much.